All right, welcome back. This is day 5 of our in-depth Postgres training, our last day. And today we're going to jump into talking about migrations, our last topic, migrations to Postgres. All right, but before I do that, just like every day, real quickly, happiness hints. At this point in time, I think we've touched on everything. Right, so multi-AZ backups and logical exports. We talked about yesterday how that's your safety kit, your most important tools to make sure that you're not going to lose data. And again, these happiness hints, what this is this the database engineering team, the Postgres database engineering team at AWS or at RDS specifically. These are the things that we don't really even debate with each other about. We're just like, oh yeah, if it's a production system, it should have this. And these are the tools that make solving problems easy when we work with customers. When we work with a customer and they've done all of these things, it really shortens the time to resolve issues. We have everything that we need at our disposal, and you'd find the same as well. So multi-AZ backups, logical exports, huge pages and connection pooling we talked about yesterday, and we were just talking a little bit more about this morning. Auto vacuum logging, talked about auto vacuum some more yesterday as well. That's really, and the logging here, oh, by the way, there is, the idea of forcing auto vacuum logging is an RDS thing, not a Postgres thing. The reason for that is that the auto vacuum daemon runs as a super user. So this kind of comes back to the only changes that we've made to Postgres is just kind of the bare essentials of what we had to do just to offer it as a managed service. And largely what that means is things around the security model, so that we could offer, because we could offer Postgres as a managed service and just not let you do anything, very little, nothing that requires super user. But what we've found is that it's a lot more useful if we find a way to allow a lot of these super user things that typically require super user to create sort of an intermediate tier, what we call the RDS super user, which allows you to do a lot of those things, like whether it's event triggers, whether it's this, controlling the logging of auto vacuum, things like that. So those are the sorts of things that's the only place where you'll find modifications. There was one time, actually, that I just pulled the Git source code for the RDS Postgres, and I just did a diff from the same version of Community Postgres to RDS Postgres, and then I just counted the number of plus signs and minus signs to just see how many lines of code were changed. And what I found when I did that, and then after that, I looked at a couple of different minor releases of Community Postgres, okay? And what I found out when I ran that comparison was that we changed less than the smallest minor version release of Community Postgres that I was able to find, or that I looked at in all of my comparisons. So that kind of gives you a sense of the scope. We really haven't changed much. Now, that doesn't include just to be clear, what I'm not including there is there are security releases. So there are a couple of minor releases that were released just to address a certain CVE, which those have 10 lines of change. So that I'm not saying we have only one line of change. I was looking at the scheduled normal minor releases. But it's kind of a metric that's kind of telling and helpful. That's not a public thing right now, anyway. But I think it's a really cool metric. Forcing auto vacuum logging. Then over on the right-hand side are more performance-oriented things like PI, EM. Please pay attention to enhanced monitoring, to the granularity that you collect things. PGStat statements, temp usage, keeping track of. In this class, one of the great things about this class is that you guys have taught me a few things, and we made our list of alarms longer. So we added those last two this week. Sorry, not the last two, the middle one, free, and the last one, sort of meaning the local, calling out local storage on Aurora, which I just had a single line before, and then adding in the replica lag. Okay. Had to do that because this is the last time I'll have the slide up for the class. For the context of you guys who I'm talking to right now too, since you guys often are working with customers and not necessarily the customer. I mean, when you are the customer yourself, like when you're setting up your own systems, of course you follow these. But I would also encourage you guys pay attention to this list as you're talking to customers as well. And like I said, these are things that we don't debate about, that we kind of think these are good practices. And this slide, this goes in every single talk that I post on the internet. So this is something that I'm kind of trying to get the message out about. Like, these are things that, like, at least me personally, as a database engineer at Amazon, these are things that I consider really best practices for your production databases on AWS. Postgres. Okay. Coming across to our topics for today. The first thing is, as I said before, we're going to talk about replication. So today is migration day. And I'm going to start with replication because I think that replication fits under the umbrella of migrations pretty cleanly. I mean, when you're migrating to Postgres, the implication there is you have an existing system, you need to move the data in sometime. Somehow, you need to move the data in. Now, replication, one major use case is migration. It's not the only one, right? So just what are a couple other reasons that we would have multiple copies of our data? And that's actually, too, just to restate, replication is the sort of the word that we typically use. What does replication mean? It just means more than one copy of your data. That's really what it means. High availability would be another common reason for replication, for having multiple copies of data. And we've talked about that earlier this week already. Another reason is moving data closer to the customer. So having your data in your application, maybe if you have customers all over the world, having a copy of your data and the application in the same country or in the same region as those customers. Another reason would be for just compute power. If the largest instance that you have available, if you need more compute power than the largest instance that's available to you, being able to supplement it by having multiple copies of data. In Postgres, thinking about, so Postgres is not a new database. It's been around for a long time. It's been around for like, what did we say, 30, 40 years or more? So the idea of doing replication in Postgres is nothing new either. And in Postgres, I think that there are sort of it's helpful to me to think about three main categories of replication. And this is how I break it down. And the first category, what I'm going to do is I'm just going to walk through all of these one at a time. And the first category that I'm going to look at is what I'm calling the SQL-based replication. So the idea behind this is that there are ways of doing replication in Postgres where you don't need anything outside of the SQL standard. And the first way is what's called the statement-based replication here. And what statement-based replication is when you're managing it entirely yourself, like at the application level. So your application sends SQL down to two different systems. And the second way here is trigger-based replication solutions. And trigger-based, the earliest production replication solutions for Postgres, which were well over a decade ago, were trigger-based solutions. So these have been around for a long time. Now you might be tempted to think, since this is the original way of doing replication in Postgres and it's the oldest, that it would be obsolete, but that's not the case. So like even within this last year, I've talked to customers in particular, like what comes to mind is a couple on our retail side who have been doing migrations from their existing platforms over to Postgres. And it made what made the most sense for them was, in spite of like the complexity and the difficulty of it, for them to completely manage the replication themselves. So they even within the past year, I'm working with people, and that's what made the most sense for them. And trigger-based solutions are absolutely still relevant. One of, I think, the most obvious use cases is for older versions of Postgres, because with trigger-based solutions, you can work on versions of Postgres that are over 10 years old, that is the only solution that works there. There are, however, some drawbacks. So as I was kind of alluding to a moment ago, the drawback of SQL-based replication is that you really have the full responsibility for this. So it's not trivial. There are like a lot of corner cases and edge cases that you need to take into consideration. There are some advantages to it, but you have full responsibility for it, and the maintenance, the monitoring, everything. The trigger-based solutions have been around for the longest in Postgres. They're probably the most well understood, and I think it's pretty widely acknowledged that there is a pretty significant overhead that comes along with trigger-based replication solutions in Postgres. So the SQL-based replication pattern, yes. So it's the thing about SQL-based replication in Postgres, and I think the most important thing is that the downsides that I'm talking about here are not something that you can just change some kind of a configuration parameter and tune, and that makes them better, because they're really inherent to like the architecture and the design, right? The complexity that you have to manage, the right amplification that happens, that's just inherent to how it's done. You have to write, with a trigger-based solution, you have to do these, you have to maintain an extra set of tables. There's no way to solve that like inside of that architecture. Now the Postgres community knows that, and the Postgres community's answer to that is actually something that a lot of databases do, which brings us to our next model, which is physical replication. So the idea behind physical replication, all right, so this will probably be kind of repeat for some of you, but the basic idea behind physical replication is that what you end up with at the end of the day is something very close to what you would get if you just literally copied the files from one server to another. I mean, that's almost what it would look like. Now this is Postgres. Oracle's like this. MySQL is not like this on RDS, to be clear. But for our purposes, that's what this is. By the way, do you recognize the screenshot? You probably do, right? Yes, in our labs in this class, we had that tool up, so you were able to see that. So yeah, bit for bit. And this does, this is page inspect. I think we were able to look at that yesterday in the lab, so you guys have seen this before, and I don't need to dig into it. It's really awesome. I think it's 10.5 and up is where you can get Postgres on RDS. So that's really exciting. So physical replication in RDS. There's actually, I think it's worth mentioning multi-AZ here as well, because multi-AZ is another form of physical replication. So multi-AZ and read replicas, these are your two forms of physical replication in Postgres. In physical replication, it solves the efficiency problem, right? It solves, you no longer have all of that extra overhead of maintaining double copies. It also solves the problem of the complexity of managing it entirely yourself. However, there are still some downsides to it, which is that, first of all, with physical replication, you can't replicate just like one table or one schema, right? You only can replicate the entire database. You can't do different versions. You can't go across versions. And the other thing is you cannot, it's read-only. You can't create additional tables in the copy. The copy is going to be the same. So we've solved the problems that we had with SQL-based replication. However, in the process of solving them, we lost all of that flexibility that we had. So what is our answer to this? The Postgres community knows this, of course, and I would say kind of this is sort of an area that's been really thoroughly explored within kind of the relational database field as well over the last decades. So the answer to this, of course, and this has been something that the Postgres community has worked on for a long time. This is not something new. However, before I kind of dive into talking about logical replication, what I'm actually going to do is step back and start at the bottom and kind of build up and look at how it works. So the first thing that you need, and the first thing where it all starts, is the write-ahead log. And we've talked about this a whole bunch this week, so you have the basic idea behind it. By the way, that lswalder command, you can actually list out your list of wall files. That works in RDS. So you do have, you have this level of probably more transparency than a lot of people using RDS realize of how much they themselves can see into the internal guts of the engine. So I won't stay here for long. You guys know what a wall log is. It's where you're putting your changes in. Now, that's going to be the foundational thing. You remember that the thing that gets us out of the trigger-based solution. This is the thing that gets us out of that. Every database has some concept like this, whether it's called a redo, whether it's called a journal. And this is kind of fundamentally, this is the missing piece of the puzzle. This is the thing that we need to avoid all the extra overhead. So this is what we need to build on. The next thing in Postgres, which is sort of the next building block that we need to have logical replication, is the idea it's this little process called the wall sender. So this was added in Postgres 9.4. And the idea was to have a process which could sit there. OK, the problem that you have with the write-ahead log, all right, the earliest versions of Postgres physical replication were just built on this. This was the original version. But the problem that you had was that you couldn't copy that wall log over to your far server until you were finished with it and started on the next one. So what that means is, so you can't just copy it over, right? Because if you copy a partial file, now what are you going to do? He doesn't have the whole thing when he starts trying to read it on the other side and replay the changes. So what that means is the original physical replication solutions for Postgres, they just had to wait before they could send the changes across. And what this did was this solved that problem. So we just added a process that could read those changes as they went into the wall log and immediately send them over the network to the far side. And that works beautifully. And with that little tiny change in Postgres, the next iteration of physical replication in Postgres was able to eliminate the lag on the replica. So in this configuration right here, Postgres can already now maintain a physical copy which doesn't have any lag at all. However, you still have a problem. And the problem now is, what if your physical replica, you have a problem and it goes offline for a while, or maybe it pauses. Let's say you have a problem and it goes offline for a while. Well, in the meantime, over here on the primary database, you have vacuum, you're working along, and he finishes up and he kind of realizes, I don't need these old wall logs anymore, so I'm going to go ahead and clean those up and send them to the backup system. Well, then you bring your standby back up, and your standby, your wall sender goes to look for the changes to send across, but now they're gone. So now you're back in the situation where your standby needs to pull the logs from the backup the old-fashioned way, start applying them from there, which is back in the sort of slow, inefficient place where we were before. Postgres' answer to that was the idea of, up there on the top, replication slots. So the replication slots is just a little bit of metadata inside of the catalog, and nothing more than that. And all that is it just a little bit of metadata that says, hey, somebody's reading this wall data, and so don't delete it yet. That's all it is. And again, that solves the problem. Now, you do need to be careful with replication slots. It is something to watch, because if you have some replica that never comes back, then you can never clean up wall, and you start accumulating disk space. So that's something you want to watch, which is one of the reasons we have a happiness hint around alarming on your disk space, because that will catch these sorts of things before you fill the disk. So what's the next layer on top? Now that we have this wall sender, and we have replication slots. Now actually we're in a really good place with physical replication. We have a great solution there. But what if we could make that wall sender process a little bit smarter? What if we could take that wall sender process, and the wall sender process, instead of just blindly sending bits over the network, what if it actually understood and could start to interpret what it was reading in that wall log? Well, that's the next layer, and that's exactly what Postgres did. Again, this is actually quite a while ago. I think it's almost been 10 years now since version 9.4 when they introduced this. So logical decoding was just a big upgrade to the brains of the wall sender process. And what it means is that the wall sender can now interpret the data that's in the wall log. It understands, and what it does, it does kind of what this picture is showing. So the wall sender process in memory, and then it can like spill to disk if it needs to, actually every time it sees a change, keeps track of which transaction that change was a part of. And then it keeps track of the status of those transactions. And you can see here, you can look, transaction number 3 on the right now aborted. It has a rollback at the bottom. See the last command there in the bottom has a letter R for rollback. So what does a wall sender do? He just throws that away. He doesn't need to do anything with that. Here, transaction number 2, and the wall sender, this is where everything is happening. The wall sender process, and you can look, you can do a PS, a process list, and you can see the wall sender process there on your database. He's tracking transaction number 2, and transaction number 2 commits. Well, once he sees that commit, he knows, okay, I could send this out now. So then he sends transaction 2, he goes to ship that over the network and to send it to somebody. But he doesn't just do that. This is where the Postgres community did something that I think was very, very helpful and clever, and also very much in the style of Postgres. Rather than just writing a little bit of code to send it over the network, they made it pluggable. So they made it so that, similar to how people can write extensions for Postgres, they can also write what we call logical decoding plugins for Postgres. Anybody can write one. And that plugin is the piece that sends it over the network. So what that means, the implication of that, is that if I'm building a service, and for my service, I want just all the changes happening in my database, and maybe I want to have those as JSON, because that's based on my language choice and how I'm working with data, that would be really easy for me to code. Well, that means I can just use the JSON plugin, and I will get all those changes over the network sent to me as JSON. Or maybe I'm sending this to a different downstream data warehouse or data lake system, and that system understands SQL. So how about if I have, it'd be great for me if I could have those changes come to me just as simple SQL statements like inserts and updates and deletes. Well, the wall sender can do that too. You just use a slightly different plugin, and all of those statements now come out as SQL statements, which can just be applied on my downstream system. So those are called logical decoding plugins, and there's a number of them that we support on RDS, and you can find a list in the docs for that. So that's the wall sender process. With all of this in place, we're now finally in a position to introduce the very top layer of the stack, which is the idea, which is really what we call logical replication in Postgres, which is the publications and subscriptions. But the one really important takeaway from this slide here is that, so this was introduced about a year ago now in Postgres 10, and it was a really big deal when they announced it. Postgres 10, logical replication. That big announcement in Postgres 10 was not like this massive development effort with like thousands of lines of code that were all merged into Postgres 10 and shipped as a new feature. It was actually just like the very top layer on top of a bunch of infrastructure that had been built like well over 10 years, that have been slowly built. And this is the way the Postgres community tends to work, that they tend to like iterate slowly across multiple major versions. And even this week, we've seen that. We saw that with wait events when I talked about those, how like the first bit went into 9.6 and then the larger block went into 10. And there's continued work in the future. We see that with partitioning. The sort of basic, the sort of essential foundational pieces for partitioning. Again, a number of them came into 10. You give tuple routing, things like that. 11 got a whole bunch more, like the hash partitioning model, the ability to do foreign keys, and the push down on the indexes, things like that. So you see this all over the place in Postgres, where they iterate across major versions and get like a core that's really stable, and continue to harden and stabilize that core, and then put these layers in on top of it and improve on it. It doesn't always make for the best marketing, but it makes for a really, really well-engineered piece of software. So I'm a fan of this. I think it's a great model. I would say that the publication and subscriptions, when they finally got around to doing that, there were kind of three big things that were left to do there. Well, three big or small, however you look at it. It was mainly what you had left, with all of the infrastructure in place, the streaming replication, replication slots were there, the logical decoding piece was there. All that we really had left was just work out the exact SQL syntax, work out a security model, and then work out, you needed something on the apply side. That was the last big piece. So something to actually receive the changes and apply those on the other end of the connection. A lot of the other stuff was already done. So reviewing, rehashing, we talked about physical replication. Read replicas are basically built on the write-ahead login streaming replication, and then slots, right? DMS, as well as a whole bunch of third-party replication solutions, are all based on logical decoding, which we got in version 9.4. And then the standard Postgres, what we think of and what we call logical replication in Postgres, is built on the publication and subscription syntax, which is the top layer of everything that I've shown here. So logical replication in Postgres. This, if you're looking for, or if you're working with people who are looking for a logical replication in Postgres, it makes all the sense in the world to start here. It's stable, it's solid, it's built into core Postgres. You don't need to install an extension or do anything, and this gives you a lot of what you need. I would also say probably there's a lot of development effort coalescing around this since it's in core, right? But there is kind of one other important thing worth mentioning, which is that in addition to this, we also support an extension called PG Logical. So PG Logical is, it just has a couple of key features that could be useful depending on what somebody's looking for. In particular, I would say sort of the one that stands out to me the most is if you need to support older versions of Postgres before version 10. You have to use PG Logical for that. So, yep. So that would be sort of a key thing. So that's logical replication. All right, and those were the slides that I had pulled together for that. And now that we've talked about getting your data into Postgres, the last thing is to talk about what to do with your data now that you have it in. So this brings us, so I'm going to spend the rest of our time today just talking about a couple other migration-related topics. Things that, so this is, well, first, I've got a couple slides here just talking about motivations for migration. So this is kind of talking through a couple of the motivators. And this is helpful. The phases that people go through. Migration is not just like I copy my data from one database to another. Like you really need to have and we should expect people to have sort of a phased plan to migration. And this is walking through some of the major phases that you would do. Migration breakdown. This is a breakdown of, what this is kind of showing is that the production cutover, like that last phase, that you think of is probably, from a timing perspective, like where you spend the least amount of energy and effort. It's an important step, but it's just the little small one at the end. The bulk of your time actually goes into a couple of other things, testing being a huge chunk, right? But then schema and application migration also being a big one. So this is just kind of level setting and getting expectations set ahead of time. It's when you look at where you end up spending your time, the one sort of other important thing that's worth pointing out is really the database piece tends to be the easiest piece to migrate. So that's actually, and I bet you guys would relate to this, a lot of the questions that you're going to get related to migration, if anything, they're going to be often SQL related. You know, like we'll get some questions about things like table spaces and schemas, but for the place where people are actually spending all of their time is they're doing an awful lot of work on their application side to try to get their application to work well with a different database. All right, the part that I'm most interested in is common mistakes, and this is going to get into just things that people often run into that are different on Postgres from other platforms. So we don't need to talk about why. First of all, kind of real simple one is just sort of the system defaults in general. It's not uncommon for people to sort of have something that they were thinking from a different database system and then just try to do the same thing in Postgres. And you don't want to do that, right? Postgres is its own database. It's different. And it's generally better. It's generally better to sort of look at the way things are done in Postgres, just learn Postgres from scratch. And there's sort of a key thing. The key thing is that you should always go with the Postgres or the RDS Postgres defaults unless you have a solid reason not to. Like, what's the common thread in both of these is that somebody was choosing a default because that was the default on the other system. So we have carefully tuned the default values in RDS Postgres to be the best defaults for Postgres. So when you have established, even if inside of your organization you established, well, you know, going to 60% of memory is the right practice for our default shared buffers in Oracle, you should not take what you figured out for your Oracle systems and just port that over as configuration settings for Postgres. You really want to start from the defaults and then work out from there. So I could totally, this is actually a very understandable thing. Like when because you did this with Oracle, right? You started with the Oracle defaults, but then you spent years running your application on Oracle. And over those years, I've done this too, you sort of learn, and this is how my application behaves. And because of my particular application, I have learned that I can significantly improve the default settings in the database for Oracle. And so it's very understandable to sort of just think that, like, well, I already figured all that out. That knowledge would apply to Postgres too, but it doesn't. It does not apply the same to Postgres. You need to start with the defaults and work from there in Postgres and prove out that your changes to the defaults are the right thing. That's looking at block size, which is another example. In Postgres, of course, you can't set the block size in RDS Postgres, but you can if you're managing on your own system. So outside of system tuning, let's look at some more application level specific things. And the first thing is case, uppercase and lowercase. So if you work on Oracle, the thing to note here, so I'm looking at a table, and I remember this, is that everything is uppercase in Oracle, right? So there's no quotes here. And these are all uppercase as well. There's no quotes there. So that's in Oracle. In Postgres, if you want things to be in uppercase, you can do that, but you have to double quote it. And that's how you would get uppercase. So if we took this schema here and we migrated this schema over to Postgres, okay, now this is what it would look like by default, right? F name, M name, and first name, middle name, last name, the same schema. But if we were to bring that over as was, and there are some migration tools that do this, you notice now I have to double quote in order to get it to uppercase, whereas previously I didn't have to, well, I was lowercase. I didn't need the double quotes. The other thing is, in addition to having to double quote the table name, I have to double quote every single column name if I want to run a query off of there, right? That gets to be really, really annoying after a while if you're having to constantly do that. So that's folding and that's case. The next area that we'll jump into is table spaces. Okay, so table spaces in Postgres. The purpose of table spaces in Postgres is really at the physical layer, right? Not the logical layer. It's there so that you can control where files are laid out. And the reason that is important is especially if you built a server from yourself, so and you're putting hard drives in that server, and then you're putting your Postgres database on that server, you want to control sort of how data is spread across the different disks in the box. So Postgres gives you table spaces in order to be able to control the layout of your things, so that you can use table spaces to map your files to different areas of storage. And it's very much related to the physical sort of storage architecture. In Oracle, same kind of concept. Oracle has table spaces as well, same history, same general purpose. Now, in RDS, okay, this is absolutely a true statement that we have on this slide here, which is the idea that it's not like schemas. I think that's sort of the important thing, is that you don't use table spaces for organization, to like organize your objects. That's not the purpose of them. Schemas are for that. Schemas are for organizing objects and separating things, but not table spaces. So yeah, so there's no real benefit unless you span multiple mount points. And in RDS, in particular, there's really no benefit. Now, we do support tables. The table space syntax will work on RDS. If you say create table space, in RDS, in the background, it's just ignoring that because it's all stored in the same place. So it doesn't actually do anything to use different table spaces. It won't break, but it doesn't actually do anything. Yep, it does, yeah. Makes things a bit more cumbersome for using table spaces on Postgres on EC2. Okay, has anybody ever heard of dual in Oracle? You've heard of it, have you?
I know both of them.
Okay. Oracle has this thing called a dual table. And all it is like basically an empty table with a single row. And the reason it's there is because in Oracle, you cannot have a SQL statement without a from clause. You always must have from. So what if you just want to, like this is the perfect example. I just want to get the current time, like the date. That's what this tells me. Well, how do you do that in Oracle is you have to have something. So they made this table called dual, which is, I don't know where that name came from. I don't remember anymore. Probably heard the story once. And that just became a thing and it never went away. And so like, this is just one of those weird things, like Oracle culture. Like everybody who's ever worked on Oracle knows about dual because it's like you have to use it all the time. If you want to call a function, get the current date and time, like there's all these things. So in Postgres, you don't need a from clause. You've seen me do this week a whole bunch of times. So you don't need that. The thing to look out for is that, what they say here, don't mock a dual table. Some people, it doesn't mean don't make fun of the dual table. That's not, you can make fun of the dual table. That's completely okay. What it means is to mock it up, like to create a table in Postgres called dual so that your queries can come across without having to change. You go change your queries is the point there. All right, exception handling. So what are exceptions? Exceptions look like this. It's in your procedural code. So in your triggers and your functions, or in your just blocks of PLPG-SQL, or other languages as well could have something like this. You can have an exception handler where if it throws an error, the exception handler handles it. This is a very common thing to do in Oracle, and this is the thing, this bottom point is the important one, that there's a lot of tools. SCT is one, Amazon's schema conversion tool, that will just take your Oracle PLPG SQL code and just try to translate that directly to Postgres. And it's just going to be very literal about bringing stuff across. They generally don't, well, they can't factor out exceptions. Exception handling in Postgres is more expensive than it is. It's just not optimized as much as it is in PLPG SQL, in Oracle's PL SQL. So in something that you want to keep an eye on in Postgres, because, and this is one of the reasons, because Postgres is going to use subtransactions to handle these. So every time that you have an exception handler in your code, Postgres has to create a subtransaction to be able to roll back the SQL inside of there. That's just how it's done. It's not optimized further than that. That can be expensive. I don't know if you remember when I was describing my benchmark that I did to try to get into a transaction ID wraparound. I was actually using an exception block just like this to do that, and running as fast as I could to see if I could get faster than vacuum. All right, differences here. Fine-tuning queries. Hints are another sort of difference that come up all the time between Oracle and Postgres. We do have a call out to those on the slide. So you guys know PG Hint Plan. There is an extension that gives you hints in Postgres. I've seen lots of people using that, so I think that's fine. But it's not part of the core code base. You definitely, I would say, you definitely don't want to just bring all your hints over from Oracle to Postgres. And you probably don't want to bring any, is the thing. Because given the differences in the MVCC model, we talked about that. So Postgres that is super unique. I don't know of any other databases that do the multiple copies of rows like Postgres does. Not any other major ones like that are sort of in wide, broad use, right? Most of the other ones use different models to do MVCC. When such a fundamental thing is different, that's going to impact. I think you have to throw all your assumptions about performance out the window when you migrate from one system to another, right? So even if you knew for sure that on Oracle, I always should use this particular index to run this query, on Postgres, you shouldn't start with the same index. Start with no hints, just like you did on Oracle, hopefully. Most people, you start without the hints. And the hints are basically something to cover a deficiency in the optimizer. That's what they exist for. And you're going to find every optimizer has deficiencies. There's always sort of circumstances where the optimizer can't get the best plan, and you're able to find one that's better. But Postgres' optimizer is different than Oracle's. They're going to be optimized and tuned differently, and you're going to find different holes in different spots that need to be fixed. So that's the slide on hints. What do we have here? I didn't index. Postgres has a lot more index types, so that's worth pointing out. Postgres, yes, this is another really cool one. In fact, this is the GIN trigram ops. If you remember from Tuesday, I kind of introduced that. And this is an example of something you can't do in Oracle, by the way. This is just kind of cool tricks that Postgres has, where they're doing like a search with a % sign on the front and on the front and the end of that query, before and after it. And Postgres is actually able to use this GIN index to process that query. Oracle has nothing. It's not able to take that kind of a query and use an index on it. You'd have to use something a lot more sophisticated to get a similar type of thing out of Oracle. OK. Next up, we talk about native features in Postgres. And this is true. It is a lot more feature-rich, or it has a lot of feature-rich for developers in particular. So a lot more stored procedures, stored procedure languages which are available. It has things like foreign data wrappers, certainly a lot more data type support. That's another huge difference between Postgres and other databases. most databases have a small number of like core data types, and then the whole data, and then you sort of build everything around those core data types. If you want to store data, you have to decompose, your application decomposes data down into that data type, those core data types, and puts it in, just your strings, your dates, your numbers. In Postgres, it's very different. You can create custom data types, you can create your own data types. That's how we have like JSON as a native data type in Postgres. And then the spatial thing too is really rich. So when you're coming over, this is again one of those things. It would not be uncommon at all. There's a lot of people migrating to Postgres. So Postgres right now, it's just climbing in popularity like crazy, right? That is definitely not all new users of databases, right? So a lot of these people coming to Postgres have prior experience on other databases, and they're going to bring a lot of those assumptions. So they know how to do things. It's like, okay, I've been building an application that figures out a route from, it figures out a route from this city to that city, and it can figure the streets and the turns. So I know how to do that, and I know how to do it on this database. So this is how I solve the problem. There are lots and lots of opportunities when you're talking with people coming into Postgres to be like, hey, let me just tell you about, Postgres can actually solve your problem this way. And this is because it has these features that maybe you just didn't know about. So tons of opportunities to sort of educate about native features in Postgres, because there's a lot there. Also a good reason to kind of just go through and get familiar with a lot of the different native functionality that Postgres has. And what are we demonstrating here? This is demonstrating where we wrote a function in JavaScript, is what that's doing, which isn't something you can't do in many other places, and that does work on RDS. Yep. Okay, this is huge.